好。
For you, it must be the evening.
Great. Excellent.
Okay, welcome everybody. I'm Robert Lipschitz from the University of Oregon, the moderator for this session in topology. It's my very great honor to introduce Yi Liu from Peking University in China. He's going to tell us about his remarkable work on surface automorphisms and virtual homological eigenvalues. There'll be a few minutes after the talk for discussion, so feel free to post questions in the topology section on Discord. If you're on Discord, and I'll ask one or two of them at the end if time allows. Now, without any further words, here's Professor Liu.
Thanks for inviting me to speak at the session. Today, I will discuss surface automorphisms and virtual homological eigenvalues. Surface automorphisms are closely related to three-manifold topology because if you look at their mapping tori, then those are naturally three manifolds, and it is the resolution of virtual Hawking conjecture and some related conjectures that provided us important tools for studying and for constructing finite covers of three manifolds. Today we're at a virtual ICM, which means that we pass online, and a virtual homological eigenvalue means that we pass to some finite cover of the surface and discuss things thereof. And here's the actual definition. So what is a surface automorphism? It just means some orientation preserving homeomorphism of a given surface. And throughout this talk, you can assume the surface to be orientable and connected and closed. That will simplify much of our discussion. Whenever you have a surface automorphism, then you can look at its induced homological actions on the first homology. Then you get a bunch of complex eigenvalues. And a virtual homological eigenvalue is associated with a setting where you have some finite cover of the surface and some lifted automorphism that commutes with automorphism downstairs. Whenever you have such setting, then any homological eigenvalue of f prime will be called a virtual homological eigenvalue. We can recall the classification of surface mapping classes, which is usually called the Nielsen-Thurston classification. According to that classification, any surface automorphism falls into one of three types up to isotopy, either periodic or pseudo-Anosov or reducible. In the last case, you can do further reductions, and eventually what you get is a finite collection of mutually disjoint, mutually non-parallel curves. You can cut your surface along those curves and get a bunch of components. Each component will be invariant under some iterates of your automorphism f, and on that component you always have pure type, either periodic or pseudo-Anosov. Then you can collect all the pseudo-Anosov components together and call it the pseudo-Anosov part. What is easy to observe is that if your surface automorphism has no pseudo-Anosov part, then any virtual homological eigenvalue of the surface automorphism will lie on the complex unit circle. And the reason is basically you can iterate your automorphism sufficiently, and eventually you get multi-dentist along disjoint curves. And obviously, in that case, all the eigenvalues will be 1. What is really challenging is the converse. Suppose your surface automorphism has non-empty pseudo-Anosov parts, then does it has some virtual homological eigenvalue that lies outside of the complex unit circle? And this is a question of Macmillan. There are some known results prior to what I'm going to talk about today. Let me just mention the following ones. First is Coberta's result in 2012. He proved that any isotopically non-trivial surface automorphism has a virtual homological eigenvalue other than 1. What he actually proved is that you can find some finite characteristic cover of the surface such that any lift to that finite cover has a homological eigenvalue other than 1. Then after that, there is Macmillan's famous gap theorem. It discovered this really surprising phenomenon that even if in the pseudo-Anosov case, the absolute values of virtual homological eigenvalues might not be able to recover the dilatation. In some cases, there will be uniform gap between the dilatation and the maximal absolute value of the virtual homological eigenvalues. You can further characterize when this happens. It happens exactly when the invariant foliations have a prime singularity of odd order. In 2017, Sun gave a criterion for the existence of nontrivial virtual homological eigenvalues. By nontrivial, I just mean outside the unit circle for simplicity, and I'll try to continue to use the word in this sense. Sun's criterion is given in terms of multivariable Alexander polynomial of the mapping torus. He shows that if that polynomial has non-trivial Mahler measure, then some virtual homological eigenvalue will lie outside the unit circle. Then in 2018, Hadari gave a positive answer to the Macmillan's question I mentioned before in the case when the boundary of surface is non-empty. He showed that if the boundary is non-empty, then you can find non-trivial virtual homological eigenvalues. And his proof also fits into the setting where you consider fully irreducible outer automorphisms of a finitely generated free group. Here is a main result of my talk. This is a positive answer to Macmillan's question. If a surface automorphism has non-empty pseudo-Anosov part, then there is some finite cover of a surface and some lift so that it has some homological eigenvalue which is non-trivial. For the rest of the talk, I'll sketch a proof of the main theorem. You can think about it a little bit, then it's easy to realize that you can reduce the general case to the case of pure type. You can assume F to have pseudo-Anosov type, and you can get rid of some trivial cases by assuming your surface to have genus greater or equal to 2. Let me also remind you at this point that we assume S to be closed. The bounded case has already been done by Hadari's results. As I mentioned before, we want to connect this problem with Riemann-Manifold topology. So the connection is given by the construction of mapping torus. The mapping torus is this familiar construction where you take your surface cross with an interval and identify any point on one end with its F image on the other end, or you can also describe it as shown on the screen. What features does the mapping torus have? Since your surface is closed and your F is pseudo-Anosov, then there is a unique hyperbolic structure on the orientable closed three-manifold MF. And this is because of the hyperbolization theorem. For example, a consequence is that your fundamental group will be a word hyperbolic group, and it is virtually special because of the virtual specialization, and we can make use of these nice things later on. Also, because of this construction, there is a distinguished suspension flow. Basically, you shift any point along the R direction, and this shifting will descend to a nice flow on the mapping torus. There is also a distinguished cohomology class in the first integral cohomology. And that is simply because you have this fibration map of F onto a circle, which is a quotient of R by Z, and then the homotopic just represents a cohomology class as above. So what we have hyperbolic geometry, and we have dynamics coming from the suspension flow, and we have homotopy or topology coming from the distinguished cohomology class. And you can put all the things together in some polytopes and the cones as shown in the first cohomology and duly the homology. These are the places where you see the important connections between different aspects. In the next few slides, I will describe the polytopes and the cones in more detail. These are important for our discussion in the sequel. First, you have Thurston norm on the first cohomology. It is a non-degenerate norm since your mapping torus is hyperbolic. And it's still called the dual Thurston norm on the first homology of the mapping torus. I consider both the cohomology and the homology to be with real coefficients. To simply put, the uniballs of the norms are polytopes, which means convex finite polyhedra, and these polytopes are linearly due to each other, and also because they arise from norm, they must be central symmetric about the origin. So you can actually see these phenomena in the pictures shown on the screen. I just draw them with Betti number, first Betti number 2, but you should imagine that if your Betti number are greater than 2, then there are some higher dimensional similar pictures that are impossible to draw on the screen. And also you should think of the grids to be due to each other. If I faithfully draw them in the same scale, then the grid, then the homological picture would be too large, so I rescaled it. So the polytopes are shown in the screen, and you can actually see they are linearly due to each other, and in particular, they are combinatorially dual to each other. That means if you see some top dimensional face on the green polytope, then you should be able to find some corresponding vertex in the red polytope, and we'll also use this nice correspondence in the sequel. Let me say one more word about the definition of Thurston norm, just for information to of experts that are unfamiliar with three-manifold topology. So the Thurston norm is you can define the Thurston norm in general for any three-manifold with boundary, and it is a norm on the first cohomology. At first defined on the integral cohomology, and then you extend it to linearly extend it to the real coefficient case. As a result, then you will get some, in general, semi-norm, which means it could be degenerate. But for hyperbolic manifolds, these are always non-degenerate norms. And for any integral cohomology class, first cohomology class, then it is Poincare due to some second or relative second homology class of the manifold. Then the definition for that class, the definition of the norm for that class is that you take the minimal complexity of any representative embedded surface, and you should think of the complexity you could think of a complexity to be just the absolute value of the Euler characteristic of the representing surface. But the actual definition is that you should first throw away some positively curved components like disks and spheres, and then you will get the correct definition of the complexity and minimal complexity and the Thurston norm. All right, remember MF is the mapping torus of a pseudo-Anosov automorphism. There are various objects associated to it, and we can try to express those structural objects in the picture. We have the distinguished cohomology class of the fibration phi f, and that is shown as a blue asterisk in the picture on the left. We cannot actually draw the suspension flow on the right. But remember, when talking about a flow, you're mostly interested in the dynamical behavior of the flow, and that is reflected by the periodic trajectories of the flow. So you can draw the homological classes of the periodic trajectories, and these are the blue dots in the picture on the right. The blue dots, as you can see, appear somewhat randomly and sporadically, but if you look along any ray emanating from the origin, the dots should appear periodically. That's basically because whenever you have a m periodic trajectory, then automatically you get km periodic trajectories by iterating that basic trajectory. Then there are some cones. First, there is a unique cone over an open face of the Thurston norm polytope that contains a blue asterisk, as you can see in the picture in green. And this cone is called the fiber cone, as introduced by Thurston. Thurston actually discovered that any primitive cohomological class in the green cone is represented by a fibration of the three-manifold over the circle. And these different fibrations are sort of equivalent to each other in the sense that they have the same suspension flow up to reparametrization. And then you can draw the linearly dual cone of the green cone on the right, and that is the red cone as I draw there. And this cone turns out to be exactly the support cone of all the periodic trajectory classes. And this cone is called the cone of homological directions. It was discovered by Fried back to the 80s. And basically, he also introduced the term homological direction, which refers to any ray in the red cone emanating from the origin. In the picture, you can also see some extra things. I draw the open face in the small black segment on the left, and it corresponds to a vertex, the white vertex on the right. And you may ask what is the relation between the white vertex and the red cone, because the red cone is not over any open face of the red polytope. And it turns out, if you look at the opposite vertex of the white vertex, and look at the corner of the norm polytope, the red polytope, at the opposite vertex, then you can see that the corner is actually affinely isomorphic to the red cone. And if you shift the opposite vertex to the origin, then the corner will just become the red cone. And this is a pictorial description of what it means by linearly dual cones in the picture. There is yet another important polytope called the Alexander polytope. So remember, for any three manifolds, you can associate a so-called Alexander polynomial with respect to any cohomology class, first cohomology class. And if you allow your cohomology class to vary, then you're able to define a multivariable version called the multivariable Alexander polynomial. And you can think of it as an element in the group ring, where the group is a free abelianization of your fundamental group. And pictorially, you can think of it. You can mark out all the grid points that correspond to non-trivial terms of the multivariable Alexander polynomial, and then the convex hull is called the Newton polytope of the multivariable Alexander polynomial, as shown in yellow in the picture on the right. And as you can see, I draw the yellow polytope within this dual Thurston norm polytope, the red polytope, and this is actually a general fact that the Alexander polytope is necessarily contained in the dual Thurston norm polytope, but it could have lower dimension, which means it could degenerate to some lower dimensional ones. But it does contain some vertices of the dual Thurston norm polytope. Whenever you see a vertex of the dual polytope that corresponds to a fibered face, then that vertex will also appear on the yellow polytope. And for our purpose, we're just interested in the vertex that is due to the distinguished fibered class. Yeah, I should also mention that the relationship between the Alexander polytope and the Thurston norm polytope, dual Thurston norm polytope, corresponds to a result of Macmillan in a paper in 2002. And next remark is that for this result to hold, you should assume your first Betti number of the mapping class group is greater or equal to 2, just for some technical reason. Okay, so with the pictures in mind, let's move on to explain the key points of the proof. Remember what we wanted to prove as the existence of non-trivial virtual homological eigenvalues. And in order to do that, as a very general strategy, we'd better have a criterion and we'd better have a construction. The criterion should tell us which finite covers will be as desired, and the construction should tell us how to find such a finite cover. Yeah, we do have one criterion in hand, that is Sun's criterion. His criterion tells us that we just have to find some finite cover with non-trivial Mahler measure of the multivariable Alexander polynomial, and we want to refine his criterion by imposing some more concrete conditions, maybe in terms of the polytopes and the geometry. Here is a preliminary version. It says that if the dual Thurston norm polytope of MF, the red polytope in the picture, has sufficiently many edges incident to the white vertex, and if the edges are all edges of the yellow polytope, then your multivariable Alexander polynomial should have non-trivial Mahler measure. Again, as you can see, this is a preliminary version because there are no finite covers involved. but stated in this way, it's pretty easy to prove. It's actually an easy consequence of a well-known theorem due to Kronecker. Kronecker's theorem was a purely algebraic one. It was about multivariable Laurent polynomials in integral coefficients. It says that if the polynomial has trivial Mahler measure, then your polynomial should be a product of cyclotomic factors. Each is in monomial of the variables. Remember in the picture, the yellow polytope is contained in the red polytope, and you can the algebraic interpretation is that if you look at the phi f grading of the Alexander multivariable Alexander polynomial, then the phi f degree should be bounded by the Thurston norm of the fiber class phi f, and that Thurston norm is equal to the number we put here, the chi-s, the absolute value of chi-s, and with this upper bound, it also bounds the number of cyclotomic factors. So if you think about it geometrically, you can see that the Alexander polytope should have at most chi-s absolute value, number of edges at the white vertex, and this contradicts the assumption that we put here. We put the chi-s absolute plus 1 or more. Okay, so this preliminary version is pretty easy to see. However, as you can see, the preliminary version is somewhat restrictive, and it does not mention anything about finite cover. We want some enhanced version, starting with some assumption on a regular finite cover, and this is the actual version that we're gonna use. So the assumption is about a regular finite cover of the mapping torus. Some similar assumption as before, and then the conclusion is that the multivariable Alexander polynomial of that finite cover has non-trivial Mahler measure. So again, Sun's criterion will apply. And the main difference of the conditions here is that instead of counting edges, we count the edge orbits with respect to the deck transformation. You can actually show that for any regular finite cover of mapping torus, there is a unique lift of the dual fibered vertex. So there is a unique white vertex for M prime, and it is invariant under the deck transformations. And you want enough deck transformation edge orbits incident to that vertex, and you also want those edge orbits to appear on the Alexander polytope, the yellow polytope of M prime. Okay, and in that way, you will be able to get non-trivial Mahler measure. The proof for this enhanced version is somewhat more notationally involved and slightly more technically complicated, but that's okay. That's still essentially algebraic. With this enhanced version, the important thing is that we have this we have somewhat concrete strategy for making constructions. First, we want to produce regular finite cover, some regular finite cover with sufficiently many virtual edge orbits incident to the virtual dual fibered vertex. And on the other hand, we want to maybe pass to some further finite cover so that we want to witness sufficiently many such virtual edge orbits with the Alexander polytopes of those further finite covers. And we'll try to realize these two steps in the next. In order to do the first step, again, let's work with some preliminary version. Suppose your mapping torus has already some number of edges incident to the white vertex, and then you want to produce some regular finite cover with at least one more edge incident to the lifted white vertex. Since you're working with regular finite cover, you can argue that any new edge will necessarily occur in some new edge orbit. So in this way, you have increased your number of edge orbits by 1. And you can try to generalize the argument and make induction and complete the first step, hopefully. So for the preliminary version, the key point of the construction is to invoke what is called virtual specialization of hyperbolic three-manifold groups and the virtual special quotient theorem. These are important theorems obtained by Agel and Weiss in the past 10 or 15 years. The virtual specialization technically gives you some finite index subgroup of a group and some action of the group on a K0 cube complex. It acts in a nice way called special action. And the virtual special quotient theorem, the effect is that it gives you some nice quotient of a given group so that you can find the finite index subgroups therein and therefore construct finite covers with properties that you wanted. So how to make use of these results? What we do is that we try to associate a finite collection of quasi-convex subgroups of the word hyperbolic group pi1 MF, and we require it to have some particular property to explain that. Remember in the earlier picture, we have this the red cone, which was called the cone of homological direction, and any ray along an edge of that cone will be called extreme homological direction. So the condition is as follows. So suppose you have any periodic trajectory that is along an extreme homological direction in its homological class, then we require that this periodic trajectory be freely homotopic to some loop in one of the quasi-convex subgroups. It seems a little technical, but we'll see how we make use of those. So what we do is that since we have this finite collection of quasi-convex subgroups, then we can invoke the virtual special quotient theorem, and basically it produces some non-elementary word hyperbolic and virtual special quotient group G, and you can require that each of the quasi-convex subgroup of your collection has finite image inside this G. So the nice thing about a virtual special non-elementary group is that it always has an infinite virtual first Betti number. So you can find some normal finite index subgroup of G with first Betti number at least 1. Then if you pull back, you find some finite index subgroup, normal finite index subgroup in pi1 of M, which corresponds to some regular finite cover. And because of the construction, you sort of have preserved all the periodic trajectories along the extreme directions, and the finite cover has a new first Betti number. Then you can see that necessarily it must have one more edge, and this edge cannot come from any of the extreme homological directions before. So in this way, you have produced a regular finite cover M prime as desired. We can promote the preliminary version to an enhanced one. This time you start with regular finite cover M prime of the mapping torus with certain number of edge orbits, and then you want to produce some new regular finite cover, some further regular finite cover with some extra edge orbits. You can actually see that the enhanced version is convenient for making inductions. The construction, essentially speaking, is the same as before. And to understand that, you need to unwrap the previous construction a bit. Remember, you worked with pseudo-Anosov automorphism SF, and typically how you work with it is that you first fix Markov partition, and then you obtain a transition graph, TF, in terms of dynamics. And then, roughly speaking, the transition graph is a finite graph with directed edges. And then the directed cycles encode the periodic trajectories of the suspension flow. In the former construction, we wanted to obtain some finite collection of quasi-convex subgroups, and roughly, to be precise, you look at the extreme rays of the Fritz cone, and for each of those, you can associate some possibly disconnected irreducible subgraphs of the transition graph. Then for each of the components, well, there is a natural map from the transition graph into MF up to homotopy. Then each of the irreducible components will also map into MF, and you can realize it as a fundamental group of some compact three manifolds mapped pi1 injectively into MF. And this is actual construction for the preliminary version. In the enhanced version, what you do is that you still use the Markov partition as before, but since you have a regular finite cover M prime, you lift that Markov partition to the finite cover. Well, you can first realize your finite cover M prime as a mapping torus for some S prime M prime. It might cover some iterate of F, and then you lift your Markov partition on S to some Markov partition on S prime. And then again, you construct transition graph T prime, and you construct corresponding quasi-convex subgroups, and then just make the same constructions. We're left with step 2 to witness virtual edge orbits. For precise statement, for any regular finite cover with any given edge orbit, you want to find a further regular finite cover M double prime such that it has some edge orbit lying over the given orbit and also lies on the Alexander polytope of M double prime. You can see that if you do this construction with respect to each of the edge orbits of M prime and take common finite cover, then you can witness at least the same number of edge orbits as M prime. Okay, so this will complete the proof of your theorem. But in order to do this construction, it's actually more involved. The key point is that you cannot make the construction directly, and you have to appeal to induction arguments. The key point is that for each of the quasi-convex subgroups we constructed, if you look at its first homology, you can construct analogous Fritz cone therein, and use that new information to extract further irreducible subgraphs in the transition graph. And for each time you extract, the Betti number of the irreducible subgraph gets smaller, and eventually you get to the cyclic case. And in that case, you can directly check the witness claim, and then you work backwards each time invoking a technical virtual retract construction in the quasi-convex subgroups of virtual special word hyperbolic groups, and then finally you can finish the construction and get M double prime of the lemma as desired. So up to now, we have explained all the key constructions of the proof. And for the rest of the talk, I want to discuss a bit about this following question. To what extent can we learn a surface mapping class through its virtual homological eigenvalues? This is a natural next step of discussion. So a brief answer to the question is that if you group the virtual homological eigenvalues in a suitable way, then you can recover a lot of information about the surface mapping class. For example, you can group the data according to the irreducible finite characters of the mapping torus. Then you are able to recover the maximal dilatation. And you can weaken the conditions furthermore, and eventually you can get some statements involving profinite surface groups and their outer automorphism groups. Here's the recent result, which roughly says mapping classes are almost determined by their finite quotient actions, and I think that's a good place to stop. Thanks for listening.
Thanks very much for that beautiful talk. We have just a few minutes. Maybe you said on last slide, I didn't catch it, but were you able to give a bound? Can you give a bound on how big a cover you need to take in order for there to be a homological eigenvalue?
That's a very good question. I don't think there's even an effective bound for that construction because it involves some induction. I didn't check every detail in there. Probably you might get some upper bound for that, but it's going to be a bad bound.
Fair enough. Are there easy examples of surface automorphisms that don't have any eigenvalues outside, like pseudo-Anosov, that don't have any outside the unit circle, but then that you can see directly, you have to take a cover?
Yes. There is a Torelli group which whose element just trivially, and you can take many pseudo-Anosov there.
Of course, that's great.
Great.
Yeah. Are there other questions along the lines that you're talking about that you're thinking about, or that you think people should think about? Other open questions that haven't been answered yet?
Yeah, I think there are some questions like determining things in terms of profinite completions, and I guess I mentioned some of those in the paper of the last theorem I mentioned there. So yeah, so I guess that's a place of reference.
Okay, perfect. That's perfect. I see we only have about 1 minute left, so thanks again for that beautiful talk. I learned a lot, and I'm sure the audience did too, and really appreciate it. The next talk in the session is in 15 minutes.
Thank you.